So, using Charles' law, it's another one of those individual gas laws, and you don't have to worry about memorizing them all because once you know the ideal gas law, Charles's law is going to be the relationship between volume and temperature. So if we're looking at the relationship between volume and temperature, that is assuming we're at constant pressure. We're a closed system, right? You blow the balloon up, tie it off, right? So we've got a constant number of moles. And of course, the gas constant is literally a constant. So you can say, okay, so volume equals nRT, rearrange to get nRT over P, sorry, doing two steps in one. And then the volume over the temperature, make a big V, equals NR over P, and that NR over P is just going to be some constant. So the ratio of volume to temperature is going to be constant, okay? So then you can take that and say, hey, the initial volume divided by the initial temperature, that ratio is going to be the same as the final volume divided by the final temperature, okay? So what would happen then is if the volume if the temperature increases, then in order to I can't even talk. In order to equilibrize the pressure, a higher temperature means the gas particles are moving with more kinetic energy, so they're moving faster, okay? So they're having a higher rate of collisions, which would result in more pressure unless you allow the volume to expand, therefore creating a longer mean free path before they collide, so that the volume will need to expand enough so that the pressure remains constant, okay? Or vice versa, if you cool it down, the gas particles are moving slower with less kinetic energy, so the volume will shrink. So think about like hot air balloons or blowing up a glove and stick it in liquid nitrogen. You get the idea of that effective temperature on volume. So it's very similar to what we were doing with Boyle's law, that if you know three variables, you know the fourth. So you've just got to assign what you have. With an important caveat, the temperature must be in Kelvin, okay? Because the problem with the Celsius and the Fahrenheit scale, which we don't really use in science, unless it's, the Weather Channel, which is the best science, right? Love the Weather Channel. So the temperature must be in Kelvin because degrees Celsius as Fahrenheit has a negative part of the scale. Of course, we don't like those temperatures, but they do exist apparently. So we have to convert the temperature in Kelvin so we have just positive numbers. Otherwise, mathematically, this is not going to work. Anywho, so the temperature must be in Kelvin is our caveat. So for this particular question, we have our initial volume and we have our initial temperature, but we're going to have to convert that into Kelvin. And then we have our final temperature. And minus 32 degrees Celsius sounds like a pretty final temperature to me. So we're going to have to rearrange and solve for our final volume. We would be expecting our final volume to be smaller because at a lower temperature, the gas particles are moving less quickly, so lower kinetic energy. So they are going to have to be in a smaller volume for the same pressure. All right, so my final volume then is going to be my initial volume times my final temperature. Yeah, that's too many X's. Divided by my initial temperature. So do be really careful with actually labeling initial, final for your temperatures, etc. People are so used to doing like P1V1 or M1V1 for like concentrations and stuff, they don't spot this. The TF is on the top here, right? So just be really careful with that. So my initial temperature was 6 degrees Celsius. You have to add 273.15 to convert that into Kelvin. So that's 279.15 in Kelvin. And my final temperature was minus 32 degrees Celsius. So again, we're going to add 273.15. So minus 32 plus 273.15 is not a good math day for me today, is 241.15 Kelvin. So those are the numbers you have to use for your initial and final temperature. Okay, so my final volume then should be initial volume, which is 17 litres. And again, unit-wise, I'm going to see that those kelvins are going to cancel out. So I'll end up with my final volume in litres, which is fine by me. The final temperature was 241.15 Kelvin, and my initial temperature was 279.15 Kelvin. All right, so get my units cancelling out as they should. Give me my final volume in litres. I'm expecting it to be smaller, so 17 times 241.15 divided by 279.15 gives me a volume of 14.7 litres to 3 significant digits. Okay, so let's have a look and see if we've got any more variations upon that. New volume of the balloon, we've done that already. They always ask us for the new volume at a colder temperature because that's essentially going to be the same thing. New volume. All right, I think these are all going to be the same. So just remember, convert temperature in Celsius to Kelvin and you should be A-okay.